So, yeah, good morning again. So, one more lecture which is in some sense similar to what we had yesterday on singular value decomposition, but also different in certain important ways. Okay. Again, handwritten slides, if you cannot read it anytime, feel free to come forward during the talk in between, I won't get disturbed, always feel free to walk to the front if it is not readable. Okay. So, this is last time the singular value decomposition was a very carefully chosen low dimensional subspace. Okay. In fact, the phrase I want to underline is that SVD is a very carefully chosen subspace. You have this singular vectors V1 to Vk in the sense that if you stop it at some 3 vectors V1, V2, V3, you get the best fit 3-dimensional subspace for the data. If you stop it at 6, then you get the best fit 6-dimensional subspace for the data and so on. Now we are throwing all caution to air, okay, and we are going to study what happens if we just take a random k-dimensional subspace and project the data into this random k-dimensional subspace. What happens? Okay, that's why the subtitle for the talk is how good is a random home. Yesterday the subtitle for the talk was which is the best fit low cost home. Okay. So, the low cost still remains the same. We are always looking for dimensionality reduction because data in very large dimensions means lot of computation on all the further processing that you do. So, usually this dimensionality reduction happens as the very first step after maybe some denoising or whatever. This happens as a pre-processing step. If you can represent in your data in a lower dimensional space, all your computations will dramatically speed up. Okay. So, the low cost still remains the same. What is different from SVD is that SVD was a carefully chosen low dimensional subspace. Now, this is the other extreme. It is a randomly chosen k-dimensional subspace. We will have to again formally define how to randomly choose a subspace, but we will see that. Okay. So, the initial setting remains the same as yesterday. You have n data points x1 to xn in a d-dimensional subspace. Okay. So, I will stick to the same symbols we used last time. Each x1, remember, is a vector. Okay. x1 is not a scalar. x1 is already something like x11, x12 comma x1d. It is itself a d-dimensional vector. You have n such d-dimensional vectors, right. Remember that each of this is something like x11, x1d. And for this to work, we need this usually when do you use a random projection? Okay, you only use it when the dimension that the data is embedded is extremely large. Okay. So, if you have something like n points, and if the dimension is already comparable to log of the number of points, you are not going to get any benefit by using this random projection, because after our analysis we will see that for random projection to work, you need something of the order of these many dimensions, what you see here. Okay. The subspace onto which you are going to project, the loco subspace, is going to have a dimension roughly 1 over epsilon squared log n. So, if your initial space was already comparable to this, there is no point in doing this. In fact, that is why this kind of a random projection is relatively new. The first time this was studied was around 1984. Compare it with SVD, which was available from 1874 and so on. So, this makes its use felt only for extremely large dimensional data, which has become common only recently. Your document term frequency vector, for example, is a classic example of a very large data. Okay. Similarly, audio files and so on. I heard that all these Spotify kind of apps use these kind of tricks to figure out which song you will be most likely to hear based on what you have already heard and so on. So, this is a relatively new technique, much younger compared to SVD. Right. Okay. So, the setting is the same. The only thing that you have to keep in mind extra is that some of our very pretty pictures that we discussed, like the Milky Way galaxy, which is how do you approximate the 3-dimensional universe on a 2-dimensional plane, those you can still ask in this setting, but it won't make that much of a sense. It usually makes a sense only when you are talking about like dimension at least 100 or so, not in dimensions 2, 3 and so. Okay. And what is going to be our key step? The original version of the Johnson-Lindenstrauss lemma essentially picked a random k-dimensional subspace. We will see how such a random k-dimensional subspace can be selected. K is still much smaller than D, and you consider this projection x onto this random space. This is this x with a vertical bar of a subspace we had already used in the last class. This denotes the projection of this vector onto this subspace Rk with some scaling. Okay, don't bother about this root of n by k. You have to really scale it so that something good happens. Okay, so this is the operation that you do. This is the random projection operation that you do. And what is the guarantee that Johnson and Lindenstrauss proved? They said that if this k, the dimension of the target subspace onto which you are projecting, is relatively high, and that high is quantified in terms of number of points and the accuracy you want, accuracy being captured in epsilon. So it is, if it is roughly more than 1 over epsilon squared log n, then something really good happens. What happens if the dimension is at least this? Then for every pair of points in your data sets, there are n points in your data sets, so you have n choose 2 pairs of data points. For every such pair of data points, their distance is approximately preserved. Okay. So what do you mean by distance being approximately preserved? If x and y were at a distance 1 meter in the original space, then after you do this projection, they will be within 1 plus or minus epsilon meters. Okay. It will be at least 1 minus epsilon meters and at most 1 plus epsilon meters. If it was 10, if the distance between some x and y was 10 meters, then it is going to be at least 10 times 1 minus epsilon. Okay. 10 minus 10 epsilon and at most 10 plus 10 epsilon. Okay. I am saying these two examples to emphasize the fact that it is a multiplicative approximation, not an additive one. Okay. The error that you will incur is also proportional to that original distance between those 2 points. Okay. So the new distance, which is this guy here, is within 1 plus or minus epsilon of the old distance, and this happens for every one of these n choose 2 pairs. Okay. So all pairwise distances are approximately preserved, and since it is a random projection, this is not a definite event, we will claim that this property happens with a very high probability. Okay. So let me repeat, what is the guarantee that Johnson's Lindenstrauss lemma gives you? Tells you that okay, you select a subspace, k-dimensional subspace at random. You don't have to do all those beautiful things you did with SVD. Just select a subspace at random, but provided its dimension is high enough, then every pairwise distance in your data set is going to be preserved with within some epsilon accuracy with very high probability. That is the guarantee. So there is some loss of accuracy, and then there is some randomness in the answer. There will be a very negligible probability that this won't happen. Okay. So this is the claim. Now this was the original setting, but maybe I'll talk about how to prove the lemma in this setting towards the end. Okay. But 5-10 years later, nowadays this is usually stated in a slightly different version, not a big difference, but what is different is there in red. Okay. The setting remains same, you have n data points in a d-dimensional space, it makes sense only if d is really large, and instead of taking this k-dimensional random subspace and projecting data onto that, you do something which is nearly the same operation. Okay. It is almost like taking a projection onto a random subspace, but not exactly. How much they differ and so on, we will discuss at the end of this lecture. Okay. But this is the modern or the newer or easier to analyze and easier to implement setting of this random projection. So what you do is you design a matrix, you don't design, in fact you randomly generate a matrix A. This matrix A it's a k by d matrix, so you have k rows and d columns. Okay. each entry in this matrix is a random variable. It is an independent Gaussian with 0 mean and unit variance. Okay. So, I hope you are all familiar with the Gaussian random variable, right? The bell curve, that famous bell curve. So, each entry in this matrix is going to be a Gaussian random variable whose mean is 0 and variance is 1. Okay, that is what I mean when I say standard Gaussian. I will recap some of the useful properties of standard Gaussian in the couple of slides later. Okay. So, this is a matrix now. Okay. It is a completely a random matrix. Every entry is independent of any other entry and each entry is a Gaussian, 0 mean, unit variance, Gaussian. And instead of doing this projection and so on, all you do is you take your x, your data point, any data point, and multiply it with this matrix. Okay. So, your result is nothing but Ax. Again, forget about the scaling 1 by root k etc. for now. That is just so that the distances are all scaled up to what they were earlier. Okay. So, now this whole projection business, projection also can be represented as a matrix multiplication, but then you really have to have a very careful algorithm to pick a uniform random subspace, to pick a random subspace uniformly from the all possible k dimensional subspace, but this is much more standard. You can implement it in a computer very easily. You just have to generate k times d standard Gaussian random variables, all your package, MATLAB, Python, whatever will have a way to generate that many independent Gaussian random variables, right. So, now the transformation has become way more simple. All you do is you generate this random k by d matrix and multiply your data with that. That is going to be the embedded version of your data point. Your x1 will be at 1 by root k Ax1, your x2, the second data point will be at 1 by root k Ax2 and so on. Your xn will be at 1 by root k Axn. Okay. Since the matrix is going to be like a long rectangular matrix, the result is going to be just a k dimensional vector instead of d, and since we assume d is much larger than log n and so on, and k is going to be roughly order log n. So, this is going to have a compressed representation of the data. Instead of each data point being d dimensional in the original setting, we will reduce it to it being k dimensional. Guarantee remains the same. Once your k is large enough, the subspace, the k is large enough, then all pairwise distances, all pairwise, okay, all the n choose 2 pairwise distances are preserved within 1 plus or minus epsilon accuracy. Okay. In this, I have, instead of saying distances are preserved, I am saying the squared distances are preserved. That is again the same trick, that makes the analysis easier. That square root in the Euclidean norm is only an annoyance, right. So, it is the same guarantee. If the squares of a distances are preserved within 1 plus or minus epsilon, its square root is also preserved within similar accuracy. Okay. So, that is, so this is the setting that we will discuss more. Okay. Originally the idea came as a projection, but later it is now stated as a linear transformation onto a smaller dimensional subspace. But it is still good to visualize for our visualization, it is still good to think of it as projecting it to a subspace. Okay. And it is very close, we will see why this particular matrix is almost like projecting into a random dimensional subspace. Okay. So, some remarks before we go further, some surprising remarks. Okay. First of all, this function, this 1 by root k a times x, which is what I refer to as f of x. Okay. F of x is just this function here. Okay. This function here is independent of x, and that is where it dramatically differs from the singular value decomposition. SVD was something which was very much data dependent, but this transformation is data independent. So, it has no understanding of the data, unlike SVD. In fact, SVD we said was still one of the best tools to understand the major correlations, the major patterns in your data. This is completely unaware of the data, because you are just selecting a random matrix, that is your function. You really did not look at the data when you were populating this matrix. Okay. So, this random projection is not really going to improve your understanding of the data, but it is still going to make all your algorithms faster. It is a very good representation technique. It will not give you any insight into the data, it will not tell you anything that you did not know about the data already, but it is a tool to really have a very low cost representation so that your algorithms everything become faster. Okay, that is the first remark I wanted to say. Another surprise is that the required dimension k for which all these guarantees will hold is independent of the ambient dimension. Okay. It only depends on n, the number of data points, and the accuracy you want, epsilon. Okay. That is also in some sense a bit surprising. Okay. So, that way this is really scalable, you really do not have to, your topic vector can have all the 100,000 words from your dictionary, it does not really matter. Okay. The dimension that you will require is only going to depend on epsilon and log n. Okay. And again, this log is an amazingly vanishing function. Think about number of data points being say 1 billion. 1 billion is what? 10 to the power 9. But still log to the base 10 of that is still only 9, right. 1 billion, once you take a log, you will get something like 9 times log 10 to the base 2, which is roughly like what, 25 or 30. So, this log n is really small. What is going to hit you most of the time is the accuracy that you demand, because even if you want 10% kind of, you can tolerate 10% error, that is saying you can tolerate an epsilon of 0.1, which still would mean you need 1 by epsilon squared will be like 1 by 100, sorry, 1 by epsilon squared will be like 100, right. So, that is still going to be the dominant term. Okay. And there was a lot of research on checking whether this 1 by epsilon squared can be improved to 1 by epsilon or so on, but now we know that this is tight. Okay. This is a very recent result, as recent as 2017, where it was shown that in fact this is not just an upper bound, you really cannot go below this 1 by epsilon squared log n is really needed for guaranteeing this preservation of all pairwise distances within 1 by epsilon squared. Okay. And yeah, this also I already mentioned, and also I want to stress the fact that we are not saying most of the pairwise distances are preserved. What we are saying is that all the pairwise distances are preserved most of the time, where the most of the time is another way of saying with very high probability. Okay. Yeah. So, with this remarks, yeah, okay. Before getting into the crux of the matter, let us also talk a bit about applications. I have already kind of hinted what are these applications. Again, remember, all these applications are there, are there even though we know that this random projection has no understanding of the data. Okay. It is something which you can blindly do on the data. There are advantages to it, because like the most common, one of the very common search in data is you represent your data in some database, a query comes from outside, you want to find out which are the nearest points in terms of this query. What are the best matches in your data set for the query that is coming in, right. It is a very common setting. You can imagine 100 applications where you will want to find which is the nearest data point to the query, right. Now, since it is a random transformation, it does not look into the data, it is good, because you had anyway no option to look at the query, right. Your query is something that will come in the future. So, it is good that this projection really is data agnostic. So, whatever query comes in, you apply the same, your A matrix is already there, you just multiply it with that, that gives you the low dimensional representation of the query. Now, in this low dimensional representation, your query is in the low dimensional representation, data points are all in the low dimensional representation, find the nearest neighbor. We have already a guarantee that these distances are approximately preserved. So, the nearest neighbor search in this low dimensional space will almost lead you with the nearest neighbors in the actual space. Okay. So, yeah, this having no understanding of the data is in some cases good, like especially when some of the data is unknown to you. Okay. But keep in mind that it only works if your algorithms only use pairwise distances, right. Like we are not claiming that some other property of the data is satisfied. Okay. So, these algorithms that should use this as a pre-processing should be those algorithms which only rely on pairwise distances, and it is tolerant, it is robust in the sense that it is tolerant to some amount of approximation to this distance. If some algorithm is critical about the distances being matched exactly, then doing a random projection as a pre-processing may be a bad idea. But even with these two constraints, you still have a lot of examples where you do this as a pre-processing, like nearest neighbor query, clustering. If you can imagine, clustering of data points, you can see that both the above conditions are satisfied there, right? What comes in the same cluster is only dependent on pairwise distances, and it's okay if there is some error in or some approximation happening to these distances. So you can do random projection before you actually do a clustering, and your clustering will dramatically speed up. If you know what are support vector machines, these are ways to classify data into, like, labeled data into good and bad. You find a maximum margin separating hyperplane. But again, the idea is very geometric. You have to have the +1 labeled points and the -1 labeled points, the good points and the bad points, let me call them, separated in some way, which is something about their distances. So that's also a algorithm which only needs pairwise distances and so on. More precisely, it only needs the distance between the convex hull of the 2 points. So those kind of things are already preserved under this transform, at least approximately. So in fact, using this JLL together with support vector machines, and if you already know of it, using kernels and so on, is also a very successful line of research. Regression also, when you are fitting a best fit line through the data, you can first pre-process it like this. Ravindran already spoke about this locally sensitive hashing, where I don't know how many of you, because he just in passing he made a remark that actually what you do is multiple random projections, and then instead of retaining the projected vectors in their real sense, you just retain their signs as +1, -1. But now you do multiple random projections, okay, that will give you a locally sensitive hashing. So all these applications are there for this technique, okay. So now, any questions so far? Okay, so far we were at the surface. Now we are going to dive deep. Okay, we will see why this is true. Why should a random projection preserve all pairwise distances? Okay, looks very counterintuitive, right? You did not even look at the data. You just took a random projection, right? And still, all pairwise distances are preserved. Okay, and the one-line answer to this is that it is really something which is very similar to a law of large numbers. When you average a lot of things, the result tends to concentrate around the mean. Okay, so this is this is entirely the reason for this happening is entirely a concentration of measure phenomenon. You have, I mean, it's good that we are on the last day also we are seeing something which was probably elaborated during the first 3 days of this workshop, right? You would have seen many algorithms where you first analyze the expected value of a random variable and then see how much is this random variable's behavior, how much is it likely to be in a small window around the mean. Okay, these results are called concentration results. You would have seen the Markov inequality, Chebyshev inequality, which gives you very weak forms of concentration, and you would have also seen the Chernoff. Did you prove the Chernoff bound by any chance? So you use that e to the power moment generating function. Yeah, so that Chernoff bound gives you a way better concentration. It gives you exponentially decaying probabilities for the random variable to deviate much further away from the mean and so on. And this Chernoff kind of inequalities, as opposed to Markov and Chebyshev, applies in a context where you add up a lot of independent random variables. Okay, when a lot of, this is the law of large numbers in some sense, when you add up a lot of independent random variables, the resulting random variable is going to be very highly concentrated. It's almost another very vague way to see this is if you have seen this result called central limit theorem. It says that under some conditions, if you add up a lot of random variables, the result will start looking like a Gaussian, and this Gaussian is in fact a very nicely concentrated distribution. Its concentration around the mean is very good. It has exponentially decaying behavior once you go further away. So this amazingly, this seemingly geometric fact, about a random projection preserving pairwise distances approximately, turns out to be a consequence of concentration of measure. Okay. So, that is the one line answer. I would not give you all the detailed calculations, but I will walk you through the key steps, so that your understanding about why this happens is clear. Okay. Yeah. So, yeah. So, we will start with the basics. Okay. Let us have a quick recap of what is a one dimensional Gaussian random variable. Okay. So, you have this particular very famous function, okay, which if you plot it looks something like the picture here, and this function, if this function becomes the probability density function of a random variable, then that random variable is what we call as a one dimensional Gaussian. Okay. This mu sitting here is the mean of the random variable or the expectation of that random variable, and oh, I forgot pi 2 sigma square. Okay. And the sigma squared is the variance, sigma is the standard deviation. This is a fairly easy to study. The PDF looks a bit clumsy in the beginning, but it's a very good. It has very good analytic properties and so on. Right? Anybody who hasn't seen this before? Oh, you haven't seen the Gaussian. Okay, then we should talk a bit more about that. Okay, so first of all, we should know that. It's okay, right? So, first thing to note about this is that it is a continuous distribution, unlike a coin toss or throwing a die. In a coin toss or throwing a die, you have only some finitely many possibilities, but this is a continuous random variable in the sense that it can take values from a continuous set. In this particular case, it can take any value between minus infinity and infinity, but not with the same probability. The probability kind of varies in this fashion. Okay. But what is drawn in this picture, this is again a very common mistake that everybody makes in an interview. What you see here in this graph is not the probability, it is the probability density. In order to, there is no point in asking what is the probability that this Gaussian will take value 5. What is the answer? 0, because it is a continuous random variable, any particular value it will take a probability 0. So, only reasonable question to ask is, you fix an interval on the real line, like say between 5.1 and 5.2, and then you can ask what is the probability that this Gaussian random variable will take a value in that range. That you will get by integrating this curve in that range. The area under this curve between 5.1 and 5.2 will give you the probability. So, in particular, the height of this curve can be much larger than 1. Okay. It is a density, it is not like a probability which is at most 1. So, the mean in this case also happens to be the highest point in the curve. It is not necessary that every distribution has that property. In fact, the peak of the curve is called the mode. So, in Gaussian it happens that the mean and mode are the same, and something like 68% of your probability is within some mean plus or minus 1 standard deviation. Okay. So, it is a very good thing. In fact, if you go to something like 3 standard deviations, I think almost 99% of the data of the probability is within some 3 standard deviations on either side of the mean, and so. It's a very well concentrated, though the picture doesn't look so, it's a very well concentrated kind of a distribution. And when you say that a random variable is Gaussian, all it means is that its probability density function is this. Okay. And do not worry if this this f of x, this expression is going to look a bit clumsy and so on. In fact, we will only use a special case of this Gaussian called the standard Gaussian or the standard normal, where the mean is 0. So, this peak will be at the origin, the curve will be shifted to the origin, and the variance is 1. Okay. So, that is the standard normal distribution with which we will be mostly spending our time. Okay. This is the one dimensional Gaussian. We already mentioned that its mean is mu and its variance is sigma squared. Okay. But these are some things which you probably always know. I mean, any first time you encounter a Gaussian, these two things you study, the mean and the variance. Okay. This property also you may study, but you may have not paid that much attention, but this is a very, very important property possessed by Gaussians, and it's some kind of a closure. So, suppose x is a Gaussian random variable, then 10 times x is also a Gaussian random variable. Okay. All that the mean remains, if mu was the original mean, 10 mu will be the new mean. Okay. If sigma was the original variance, then 100 sigma, not 10 sigma, 100 sigma will be the, sorry, if sigma squared was the original variance, 100 sigma squared will be the new variance. In fact, the standard deviation scales according to what we multiplied with, the variance will scale according to the square of it. Okay. Similarly, if x was a Gaussian and you add a constant to this Gaussian, it only kind of shifts the curve along the x axis. The result is still a Gaussian, the variance does not even change, the mean gets shifted by the constant that you added. These two properties are together mentioned, together described in the first line. Okay. If x is a Gaussian and you consider something like ax plus b, where a and b are real numbers, constant real numbers, the result is also a Gaussian, the mean and the variance will change as written here. Okay. Second important property is if you have two Gaussian random variables x1 and x2 which are known to be independent. Okay. Remember, our matrix is going to be full of independent Gaussians. If you have two independent Gaussians, you add them up, you again get an independent Gaussian, I mean you again get a Gaussian. This is a very rare phenomenon. Okay. Not many distributions have this kind of a phenomenon. For example, if you think about throwing a die, okay, the distribution is going to be, the probability is going to be 1/6 for all the 6 possible outcomes, right. But if you now throw 2 dice independently and then ask about the sum of the throws, okay, then it is no more going to be a uniform distribution. Okay. The sum is more likely to be around the center values like 7, 8 and so on. It is very difficult to get 2 or 12, because you will get a 2 only if both the dice come up with 1. You will get a 12 only if both the dice come up with a 6, which are probability 1/36. But you can get a 7, for example, if the first one is a 1, second is a 6, first one is a 2, the second is a 5, or 3 and 4, or 4 and 3, or 5 and 2, or 6 and 1, right. So, I think there are something like 6 possibilities for this to happen. So, you have 1/6 probability of getting a 7. Okay. So, you add up 2 uniformly distributed random variables, the result is not uniform. In fact, it will have more like a triangular shape. So, the fact that Gaussians remain a Gaussian even if you add 2 independent Gaussian is a very critically useful property. Okay. In fact, this is also one of the secret reasons behind why central limit theorem is true. If the sum of a lot of random variables has to converge to something, that something has to be something which does not change when you add it further, right. Because if you are taking a sum of lot of things, the sum of the first half will converge to a Gaussian, the sum of the second half will converge to a Gaussian, which means the total sum is sum of 2 Gaussians, it better converge to a Gaussian. So, this property that sums of independent Gaussians remain a Gaussian is very important. Okay. Now, let us put property 1 and 2 together and you will get a much general property, because now I am going to say that linear combinations of independent Gaussians is also going to be a Gaussian, right. So, you take this x1 is a Gaussian, x2 is a Gaussian, xk is a Gaussian, and they are all mutually independent. Alpha 1, alpha 2, etc., alpha k are just scale factors, real numbers. You scale them and add them up. While scaling, because of property 1, since x1 is Gaussian, alpha 1 x1 is also Gaussian. Since x2 is Gaussian, alpha 2 x2 is also Gaussian. Now, since sum of Gaussians are Gaussians, this total sum is also a Gaussian. Okay. This is a critical property, irrespective of its use in Johnson, Lindenstrauss and all. Please try to remember this, that Gaussian has this very special property that it is closed under linear combinations of independent Gaussian. Independence is important. If it is not independent, yeah, we can say something, but let us not get into that. Everybody clear? Okay. Now, we will take Gaussians to higher dimension. It is not a scary object, it is something, if you have not seen it before also, it is something you can understand very easily. Okay. Now, we are not talking about a random variable, we are talking about a random vector. Now, like any other vector, vector is just in our computer science view of a vector, you have to just think of it as a list of numbers. Okay. So, that is a deterministic vector. Now, what is a random vector? Each of entry in this list is now a random variable. Okay. So, that is what a random vector is, okay. Fairly easy object to define. Okay. Each entry is a random variable. Okay. Now, what is this spherical Gaussian? Each entry is going to be a one dimensional Gaussian, okay. And moreover, all these one dimensional Gaussians are going to have 0 mean and the same variance, okay. I will keep it even simpler and I will call it standard spherical Gaussian and I will make that variance as 1, okay. So, the random vector that we are going to talk about, each entry is a standard Gaussian, okay, or a standard normal, which means just that it is a 0 mean unit variance Gaussian. So, that is a random vector and this random vector is said to be this is just a name that you give to it, a standard spherical Gaussian in d dimensions, okay. We will, the standard Gaussian, I think I did not highlight enough, this is the notation that we had used for Gaussian, okay, n for normal. N, the two parameters, the first parameter denotes the mean, the second parameter denotes the variance. So, the standard Gaussian will be n01. The spherical Gaussian, in its notation we have introduced this extra term called d, okay. It tells you what is the length of the vector you are talking about, okay. And these Gaussians are independent. Now, if you want to study the probabilistic behavior, the statistical behavior of a random variable, in the discrete setting you study its probability mass function, or in a continuous setting like this we study the probability density function. For a random vector, the equivalent thing is called a joint probability distribution. So, here the probability distribution, the density will no more be a curve that you can draw like this, but if it is a two dimensional vector, the domain itself will be the plane and the curve will look like a a sheet or a canvas over this plane, okay. So, that is the picture for a two dimensional random variable. What is the density? Density is no more a function of one variable, it is a function of a ordered pair. So, you will have to imagine it as a sheet floating on a surface, okay. And in the case of a two dimensional Gaussian, it will really have the shape of a bell, okay. This is in fact, if you can look, oh, I think I moved to the wrong slide, I should have gone back, okay. If this is the one cross section of a bell, you think of rotating it around and you complete the whole bell, like the church bells that you see on top of some old churches. It's that shape of a curve is what will be a two dimensional Gaussian. Imagining a three dimensional Gaussian is tricky because you need a four dimensional imagination to imagine a three dimensional Gaussian, because the domain is already three dimensional and the density is another real number which you have to represent somehow, okay. So, visualizing is hard, but roughly this is what a high dimensional Gaussian is, okay. And you also know, again I will not go too much into this, once you have independence then the joint distribution is very easy to find. It is going to be the product of the marginals, product of the individual distribution. So, if you know, since you already know the distribution of a one dimensional Gaussian which we had in this slide, all you have to do to find that of a two dimensional Gaussian is multiply fx of, let us say, what is the joint distribution at some point x1 comma x2, it will be this function at x1 times the same function at x2, because it is the same function, right. So, if you, that is what, and if you like write it out you will get this, right. So, maybe I will try to, so this was, this first guy here will be something like 1 by root 2 pi there should be a sigma, but sigma is 1, and then e raised to minus x1 minus mu, but mu is 0. So, minus x1 squared by 2 sigma squared, but sigma is 1. So, by 2, this is what fx of x1 would be. What would be fx of x2? The same thing, 1 by root 2 pi e raised to minus x2 squared by 2 and so on. What would be this guy? 1 by root 2 pi e raised to minus xd squared by 2. Now if you multiply all of this root 2 pi comes d times, so that is where you get the 2 pi to the power d by 2, or it is root 2 pi to the power d. And what happens to the things in the exponent? E raised to a times e raised to b is e raised to a plus b. So everything gets added up. So it will be e to the power minus of, this is 1 by root 2 pi to the power d, and e to the power, let me pull this minus half out, and then you will get x1 squared plus x2 squared plus etc. xd squared, right? What is that? x1 squared plus x2 squared plus 0, that is a norm of x square. Okay, so that is why we have written it in the norm form. Okay, norm of x squared. Okay, so you should never try to why I did this derivation is to tell you that don't try to remember all these complicated expressions. The single dimensional Gaussian you have to remember, you just have to multiply it with putting the appropriate arguments x1, x2, etc. instead of x to get what this is. Okay, so this is the spherical Gaussian, the higher dimensional Gaussian. This is not the most general higher dimensional Gaussian. You can have dependent variables also, in which case something will get slightly more interesting. Okay. Now this particular Gaussian, the spherical Gaussian, has a very useful property, which is that if you look at its joint distribution, it is a function of this vector, right, x1, x2. The x that is here is in fact a vector x1 is a d-dimensional vector. Okay. So f of x, the value depends on x1, x2, x3 and up to xd, true, but the dependency is only via the norm of the vector x, right. If you look at the thing, right, so if you think about two vectors with the same norm, okay, the density is going to be the same there. So let's say do this imagination in 2D. Okay. So what are all the vectors whose norm is 1? The points on the unit circle. So now if you imagine the Gaussian density curve, the two-dimensional spherical Gaussian density curve, along this circle the height is going to be the same. Okay. So if you do a contour plot, you are going to get this unit circle. This distribution is going to be the same height at the unit circle. Now look at all the points whose norm is 4 or 2, right. That would be a circle whose radius is 4 or 2. There also the height of this density is going to be the same. So there is this circular symmetry that you see. Okay. Another way to visualize it is that this bell, if you kind of rotate around the origin, doesn't change. Okay. It has this circular symmetry. Okay. This only happens because all the components were of the same variance and independent. If the second dimension had a larger variance, this bell will look like it is stretched, it is elongated on that second dimension and slightly shrunk on the first dimension. But since it is all the same variance, you have this circular symmetry in 2 dimensions, or more generally you call it a spherical symmetry in higher dimension. In 3 dimensions, what we are saying is that you cannot really imagine the plot because the domain is already 3D, but all the points on the surface of a sphere centered at origin of whichever radius. Okay. But once you fix the radius, all those points are going to have the same density. This is why it is called spherical. Okay. It is in fact, it should have been more elaborately called a spherically symmetric Gaussian, but since that is a very long phrase, people call it a spherical Gaussian. Okay. So at least the 2-dimensional spherical, do you have it in mind? It is a very circularly symmetric bell, like a church bell you can imagine. Okay. Now because it is spherically symmetric, there is lot of use to this spherical Gaussian. Like for example, if I want to sample a uniform direction in 3D space, okay, I want to sample, which is essentially saying I want to sample a unit vector which is uniform on the sphere. Okay. One way to do that is to take 3 standard normals, take a random vector x1, x2, x3, where x1, x2, x3 are independent standard normals. So you will get this vector some x1, x2, x3, just normalize it by dividing it by the norm. It will give you a unit vector who is equally likely to be in any direction, and this is extremely a useful construction. This is the most common way to sample a point uniformly from a sphere. and this works in spheres in any dimension. For 2 dimension you do not need to do it, you can just take an angle that is uniformly distributed between 0 and 360, but a similar trick does not work for 3 dimensions or higher. Okay. Now, something which is relevant to us, okay. This is not so popularly known. We want to study, we would like to study how is the norm of a spherical Gaussian distributed. We know fully how is each component of a spherical Gaussian distributed. Each component of a spherical Gaussian is a standard normal, right, and components are independent, but we would like to study how is the norm, or if it is easier to analyze, how is the norm squared of the spherical Gaussian distributed. Okay. This is where our addition of multiple random variables will come in. Okay. In between I said that, you know, what are the random variables which have very good concentration, those are which arise by adding together a lot of smaller random variables. Okay. So, here also you will see a similar pattern. Okay. So, this X that we have is a d-dimensional spherical Gaussian, each component being standard normal, independent, all components are independent. What is its norm squared? It is x1 squared, the definition of norm squared, right, x1 squared plus x2 squared plus etc. xd squared. Okay. So, this is not sum of d Gaussians. If it was sum of d Gaussians, I can finish the talk in another 5 minutes. Why? Because it is going to be another Gaussian, but it is the sum of d squared Gaussians. Squared Gaussians are far from being Gaussian, in fact they never take a negative value. Square of any random number will not, any real number will not be negative. So, this is not going to be a Gaussian, it is going to be something else. In fact, it has a name, it is a very famous distribution, it is called the chi-squared distribution with d degrees of freedom. Okay. If you add up d squares of d standard Gaussians, what you get is named as a chi-squared distribution, but that is only a name, you do not really understand anything by giving it a name, but I still put the name so that you can search for this distribution. So, when you are faced with a new random variable, often the most easy statistic to study is its expectation, its mean. So, let us start with that. Okay. If you analyze what is the expectation of this norm of x squared, which I represent as y, another random variable y, that is easy because it is a sum of something, and expectation has this property called linearity of expectation. Expectation of a sum is just the sum of expectations. So, use that, you can represent this expectation of y as e of x1 squared plus etc. Now, what is e of x1 squared? E of x1 was the mean of the standard normal, which is 0, but I am not asking what is e of x1, what is e of x1 squared? Anybody? I already got one answer, but I want you to think, this is critical. What is e of x1 squared? It is called the second moment, but in this particular case, since the mean is 0, it is also equal to, this is also equal to e of x1 minus mu1 square, right, mu1 is 0. Now, do you realize what this is? This is the variance. We already know what is the variance because it is a standard Gaussian, its variance is 1, right. Same thing with e of x2 squared, it is a second moment, but since its already mean is 0, it is the variance. So, it is sigma 2 squared, which is also 1. So, all these terms are 1, you are adding up 1 d times, so you get d. Okay. So, this norm squared of the spherical Gaussian, we do not understand it yet, but we know that its mean is d, okay, its expectation is d. So, if you add up d many squared standard Gaussians, you get a random variable whose mean is d. You also know that it is a positive random variable or a non-negative random variable, because you are adding squares of real numbers, it will never be negative. Okay. So, if you guess, okay, now the picture here surely uses more information than what we have derived, but this is roughly going to be the shape. Okay. It is not a bell curve, it is not that I could not draw the bell curve neatly and so it turned out to be like this, no. It is something which is limited onto the positive side, its mean is approximately going to be around the d mark if you are adding up d squared Gaussians. Okay. Now, for almost every application of this that you would have seen in this algorithms designed using random variable, once you study the mean, the next important question is to study how is this random variable concentrated around the mean. Okay. So, here I will not prove it, but we will use this result. Okay. So, we already know the name of this resulting distribution chi-squared with d degrees of freedom. We know its expectation, which is d. What I am interested now is to quantify the fall, quantify the slope of this curve, quantify how fast this distribution tapers down once you move away from the mean, or equivalently how much of the probability is concentrated in a small window around the mean. Okay. So, there I will, without proof, I will use this inequality. Okay. This is very much in spirit, in notation, it is very much like the Chernoff or the Hofding bound that you have seen. You see an exponential decay on the right side, and what you are studying is also the same. Let me read it out. Okay. Probability that the magnitude of y minus d. So, you expect y to be around d, okay, and magnitude of y minus d is because you consider deviations either to the left of the mean or the right of the mean as the same. So, that is why you put the magnitude of y minus d to be larger than something. Okay. That probability is going to be smaller than something. This is how every concentration bound will be stated. The probability that the magnitude of your deviation from the mean is larger than something is going to be smaller than something. Okay. So, here and then what this larger than what, smaller than what, all depends on how you do the proof for this. Okay. So, in this case, the particular result that we will need is that the deviation being larger than some epsilon times d is going to be upper bounded by 2 times e to the power minus epsilon square d by 8. Okay. What is key thing is that there is an e to the power there. Okay. That's the exponential decay. That's why we call it Chernoff like or Hofding like. If it was only some 1 by some quadratic, then we will call it Chebyshev like. Right. If it was just 1 by some linear term, we would call it Markov like. This is exponential decay, so we call it Chernoff like. Okay. In fact, if you do a small substitution, if you replace epsilon with something like beta over square root of d. By the way, I did not tell you the standard deviation of this random variable, this chi-squared with d degrees of freedom, happens to be square root of 2d. Okay, or rather the sigma squared of y, it happens to be 2d, or the standard deviation is square root of 2d. Why did I say that? Usually we study concentration in steps of standard deviation. Okay. We are talk about if you move 2 sigma away from the mean, then how much does the probability fall. So, that is why the correct window size for studying concentration is always the standard deviation, not the variance, okay, the square root of the variance. So, here like if you are really doing statistics, you would not be bothered about a epsilon d kind of variation, you would rather be bothered about some constant times square root of d variation, because the standard deviation is like square root of d. So, that is why I have rewritten the same inequality in the here. So, by just a mere substitution, if I substitute epsilon to be some beta by root d, okay, then what do I get? If I plug it in, this epsilon d becomes beta times root d. So, it is some beta times the standard deviation. Okay. I could have used 2 root d here, but yeah, then I will have to adjust this something here. Okay. But then that is only a constant deviation, so do not worry about that. So, some beta times order of standard deviation falls like 2 to the power e raised to minus beta square. Okay. So, 10 times the standard deviation would be like 2 to the power e raised to minus 100 by 8. So, this is the way to remember, like I mean if you need a qualitative picture of concentration, the picture that you should have in your mind is, if you move some beta standard deviations away from the mean, how much does the probability fall. Okay. So, here it falls exponential in beta squared, which is really good. Chebyshev would say you will fall like 1 by beta squared, which is not that good. Okay. We will use the green version for our purpose. Okay. It does not give that much of a qualitative understanding, but that keeps the computations simpler. Okay. So, as I told you, it is a Chernoff-Hofting norm. Okay. And by the way, we are still studying the square of the norm. You can also study the norm itself. It will be the square root of a chi-square distribution, slightly more ugly behaved. Its expectation will not be exactly square root of d. Okay. In fact, the fact that a square of a random variable has expectation d does not mean its square root has expectation root d. Okay. Otherwise, you would not really study a second moment, right. Your second moment would be square of the first moment, which first moment is the expectation. But it turns out that if you study the norm, I think its expectation of norm of x is, if I remember correctly, it is roughly square root of d minus 1. Okay. So, there is an additive error, but it is roughly like square root of d, and you can have a similar concentration result for directly the norm, and that is known by a famous name. It is called the Gaussian annulus theorem. That is because you are talking about a spherical Gaussian and you are going to say that the norm is concentrated around d, which means, again, imagine the two dimensional Gaussian for now. If the norm is concentrated around d, that means this distribution has its maximum probability on a circle whose radius is not d, circle whose radius is root d minus 1. So, that is like a ring around a circle whose radius is root d minus 1. This ring is called an annulus. So, that is why it is called the Gaussian annulus theorem. Most of the probability of a spherical Gaussian is concentrated on an annulus whose radius from the center is like root of d minus 1, and this is true. D here is the dimension. Okay. So, for 2 dimensions it will be root of 2 minus 1, root 1. It will be around the unit circle. For some 100 dimensions it will be more like a annulus in the 100 dimensional space whose radius from the center is around 10. Okay. So, we are going to roughly make use of this to finish our analysis. Okay. So, back to our random projection. Okay. So, this was our digression. We recapped the one dimensional Gaussian. We said we will restrict to the standard Gaussian, 0 mean unit variance, and then we stacked some d many of these independent Gaussians to get a Gaussian random vector, gave it a name called spherical Gaussian, and also kind of saw why it is called a spherical Gaussian, because its probability density function has a spherical symmetry. You rotate it, it does not change. We know that its expectation is going to be the squared, and then we studied the norm squared of the spherical distribution. We saw that its mean is d, the number of Gaussians that you are there in the vector d, and we saw that it is fairly well concentrated around the mean. That is what we have done so far. Now, we are back to our random projections. Okay. So, remember what was our matrix A? It was a k by d matrix with each entry being a standard Gaussian. So, each row you can think of as a d dimensional spherical Gaussian. Each column you can think of as a k dimensional spherical Gaussian. Okay. We will use the first picture. We will think of each row as a, let me see. Okay. We will see which picture we will use when we get there. Okay. And the mapping that we are going to do, f, is nothing but multiplication of your vector with a and then a scale factor, okay, that 1 by root k scale factor. Okay. Now, what we have to show is that pairwise distances are preserved, approximately at least. But now let us simplify the problem a bit and focus and ask this question: take some arbitrary vector x, okay, and now under this projection this x will go somewhere. How does the length of this new vector compare with the old vector? Okay. So, think of this x as a candidate for one of the n choose 2 pairwise vectors. The analysis is going to be the same for each of the n choose 2 pairwise vector, but now we are going to keep things simple. We are not going to worry about all the n choose 2 pairs. Pick one such vector. Maybe it is the difference between x2 and x1. Okay, that is what I call as x. Okay. So, imagine a single vector x, and we are now going to study how it is going to behave after you do this mapping. Okay. What do we ideally want to show? We want to show that the length of this vector is approximately preserved by this mapping, or the length squared of this vector. Since it is easier to analyze, we will show that the length squared of this vector is approximately preserved under this mapping. What do you mean by approximately preserved? If norm x squared was the original length squared, after you do the mapping f of x and take its norm squared, the answer should be within 1 minus epsilon of the original length squared and 1 plus epsilon of the original length. Okay, this is an interval. What I have written with this square bracket is the interval, like we write the interval AB of real numbers, right? All numbers x which are between a and b. We want the length squared of the mapping to be within this interval, 1 plus or minus epsilon multiplicatedly away from the original length. Okay, that is our aim. Now, to keep our notation simple without any loss of generality, we can assume that x is a unit length vector. That is the advantage you get, because you are only targeting a multiplicative approximation, because also remember that your Ax is a linear map. So, if instead of x, if you replace it with some 10x, just that the answer is also going to be multiplied by 10. The answer will be 10 times f of x. Okay. So, you can just focus on unit length vectors and later scale it to the vector that you need. So, if you are studying a unit length vector, assume x is a unit length vector, what is the allowed range for now f of x norm squared? It is 1 plus epsilon times norm x squared, which 1 minus epsilon times norm x squared, which is 1, comma 1 plus epsilon times norm x squared, which is also 1. Okay. So, every unit vector you want to be in this interval, 1 minus epsilon to 1 plus epsilon. If every unit vector falls in this interval, every vector will fall in this interval, because it is only a scaling up. F is a linear map, 10 times f of 10x is equal to 10 times f of x. Is this small assumption clear? Okay. Yeah. So, restating what we are going to do, we are going to study the case of what happens to this projection for a unit vector x. X is a d-dimensional vector and it is a unit vector. Okay. Okay. Now, it is time to use our matrix views and so on. Okay. So, buckle up. Remember, f of x is 1 by root k times a times x. Okay. So, now I am imagining a as a stack of rows. That is my freedom. I can imagine it as a pile of columns, or as a stack of rows. I am imagining it as a stack of rows. I am calling them a1, a2, etc., ak. X I am retaining as such. Now, it is a matrix vector multiplication. We have multiple ways to view it. I will use the view wherein each entry of the result is treated as an inner product of a multiplication between a row of a and x. Okay. So, the first entry in the answer is going to be the first row of a, which is a1 inner product with x. The second entry in the answer is a2 times inner product of x, and so on. 1 by root k I have not touched, the scale factor is as it is. Okay. Now, let us focus on one guy here. What is this a1 inner product with x? Okay. I am just expanding out the inner product here. a1x is a1, remember, is already a vector. It is a11, a12, etc., a1d. So, okay, why did I write k? It should be d, right? Yeah, sorry. This is correct. This is 2 only. This should be d. Yeah, because this is a k by d vector. Yeah, that is the only place I have to correct. Okay. I am just expanding out the inner product. But now, let us interpret that inner product by thinking what these guys actually are. What is x1, x2, etc.? What kind of objects are they? No, x1, x2 are not even random variables. It is a particular, it is a component of a particular vector we chose, right. These are just components of a unit vector, right. In the previous slide, remember, x was just a vector. It is an arbitrary vector. We are studying what happens when an arbitrary vector is projected using this function f. So, x1, x2, xd are just real numbers. They have one good property, that if you square them up and add, you will get 1. Other than that, these are just a set of real numbers with that property. So, x1, x2, etc. are real numbers, scalars. Whereas, what are a11, a12, etc.? Yes, they are entries from this matrix. And how did we create this matrix? Each entry was a standard Gaussian. So, a11 is a standard Gaussian, a12 is another standard Gaussian, in fact independent of a11, because all the entries in this matrix were independent Gaussians, right. Similarly, a1d is also an independent Gaussian. So, what is this whole sum? Yeah, in fact, it is a linear combination of independent Gaussians. And remember, that was one of the key properties I kind of emphasized to death, right. Linear combination of independent Gaussians is also a Gaussian. So, this whole inner product, this guy that we are studying here will also turn out to be a Gaussian. We have to analyze what is its mean and what is its variance, okay, but it will be a Gaussian. Now, what is its mean? It is easy to calculate, it is just use the linearity of expectation, right. Your E of this guy will be just E of this guy, which the expectation goes inside the sum because of linearity of expectation. So, it will be x1 is a scalar. So, this will be x1 times E of a11 plus x2 times E of a22. Remember, x1, x2 are not random variables, okay. xd times E of a1d, right. Now, what is E of a11? 0, because it is a 0 mean Gaussian. E of a22 is 0. So, this whole thing boils down to 0. Okay. So, the resulting Gaussian's mean is 0. Are you with me? Okay. You are adding some 0 mean Gaussians, the result is also going to be 0 mean. Now, let us calculate what is the variance of this resulting Gaussian. Okay. So, here okay, I should have probably mentioned it. If you add two random variables, the variance necessarily does not add. Okay. For example, if it is the same random variable, if you add x to x, you get 2x. What is going to be the variance of 2x? It is 4 times the variance of x, not 2 times the variance of x. So, variance in general does not add up, but if the what you add up are independent, then variance adds up. Okay. It is easy to show. I mean, you just write the formula for variance, right. I mean, let me assume 0 mean, so that it is easy, right. So, sigma squared of some x plus y will be expectation of okay, which is expectation of x squared plus y squared plus 2xy. I am assuming Ex is equal to Ey is equal to 0, which is the case that we are considering. So, this will be E of x squared, which is sigma squared x, plus E of y squared, which is sigma squared y, because they are 0 mean guys. E of x squared is its variance, plus 0, because twice E of xy, since they are independent, only because they are independent, we can write it as Ex times Ey, both of them are 0. Okay. So, variance will add up for independent random variables, not in general. But thankfully, our Gaussians are independent and hence variance will add up. More correctly, for variance to add up, you do not need full independence, pairwise independence is enough, okay. But we have more than that. So, variance will add up, right. But now, what do they add up to? What is the variance of x1 a11? A11's variance was 1, right. If you scale it with x1, what is its variance? X1 squared. Okay. So, this guy has a variance x1 squared, the next guy has a variance x2 squared, and so on. So, when these variance adds up because of independence, this is what you will get, right. So, suddenly the norm kind of comes in. Okay. This is nothing but the norm of x squared. We use this even to derive the joint distribution thing, right. And what is norm of x squared? 1, because we are taking a unit vector. So, finally, after all this thing, this is the key takeaway from this side. Okay. Each entry in this matrix is a standard norm. similarly the second guy is also a standard normal. Each guy here is a standard normal. Okay. So, after you do this mapping, okay, you are taking this random matrix and taking some arbitrary deterministic unit vector, and you do this mapping, you end up getting a vector all whose entries are standard normals. Are they independent? You know, is there an independence between this and this and this, etc.? Think about it. What are the random variables that come together and make the first entry? They are all the random variables in the first row of A, right? What are the random variables which mix together and make the second entry of the answer? Yeah, the random variables from the second row. Are they independent? Right, because in our matrix, random matrix A, every entry there is full mutual independence, right? So, all the random variables in the first row are independent from those of the second row and so on. So, the answer that you see here, it is not just that each entry is a standard normal, they are also mutually independent. Okay. So, we are in very, very good shape so far. Okay, this is in some sense the simplest we could hope for, and all this we got by assuming that the entries in the matrix are standard normals, nothing else. Okay. So, yeah, the first line is the summary of the previous slide. This is our mapping f, A times x, okay, and the scale factor is still there, I have not touched it. I just have given a name to each entry in the result. Okay. Each of this inner product I am respectively naming them y1, y2 up to yk, right, and we already mentioned that these y1 to yk, each of them is a standard normal, and also they are all mutually independent. Okay. So, now we are ready to study what we wanted to study. We wanted to study not the norm of f of x square, okay. That is what we want to be inside a window of 1 minus epsilon, and right, this is the guy that is we are studying in, right, and we hope, we wish that this is an element of 1 minus epsilon, 1 plus epsilon. Okay. Now, let me just take this root k to the other side and square it and then consider the norm. So, that on the right hand side I just do not have any scale factors, okay. Or like okay, maybe you can do it in 2 steps. What is norm of f x squared? You have your f of x written here, right, this is your f of x. If you want to find the norm squared of this vector, it will be y1 squared plus y2 squared plus etc. yk squared, and because there is a 1 by root k scaling, the norm squared will have that 1 by k. All I have done is that I have taken the k to the left side, okay. So, that the right side is now y1 squared plus y2 squared plus yk squared, and we already know what distribution is, right. The name of this distribution is a chi-square distribution, this time not with d degrees of freedom, because there in the primer we were looking at d dimensional Gaussian vectors. This is a k dimensional Gaussian vector, we have already projected it into a k dimensional space. So, this is sum of k squared standard Gaussian. So, this is a chi-squared with k degrees of freedom. What do we know about it? We know what its expectation is, right. Its expectation is k, the number of things you add up, but it is the expectation of k times norm of f x squared. So, what would be the expectation of norm of f x squared alone? Without the k, you can actually strike out this k and you will get a 1. Okay. We are in good shape, because I want norm of f x squared to be within 1 minus epsilon and 1 plus epsilon. The mean is sitting right at the center. Okay. The expectation is at 1. Think of this interval as 1 minus epsilon, 1 plus epsilon, and this is where we would like our norm of f x squared to fall. Thankfully, the expectation of norm of f x squared is sitting right at the center, which means we are so far so good. But now we also need to argue that it is really concentrated around this mean. Okay. So, for that we are going to use this, anyway I did not prove that, by the way, the proof of this goes almost in the same way as you would proof a Chernoff bound. You will take the exponential generating function, apply Markov to the e raised to this, just that the analysis is a bit more complicated than what you will do with Bernoulli random variables. No? Chernoff, you would have probably proved it for sum of Bernoulli random variables, right? Yeah. So, this is like a sum of squared Gaussians. So, the moment generating function, the template of the proof is same, but the actual substitutions that you do will be different. Okay. So, I am copying that concentration there. The probability that this random variable k times norm of fx squared, which is the chi squared with k degrees of freedom, will deviate from its mean, which is k, in magnitude by more than some epsilon k, is at most 2 to the power minus epsilon squared k by 8. I am just copy pasting the previous thing, right. Now, I will just cancel out k from everywhere here, right. I can cancel out the k from everywhere here and I get what I am after, right. The probability that this f of x squared, this random variable that I am studying, will deviate from 1 by more than some epsilon, which means the probability that it will either go here or the probability that it will either go here or here. That is what this red probability is, right. So, this will be some random variable which may have a curve which looks like this. We are talking about this area plus this area, okay. The probability that this area plus this area, which is the probability that this random variable fx norm squared will go into that area, is at most twice e raised to minus epsilon squared k by 8, okay. Remember that k is going to have some factor like 1 by epsilon squared log n and so on. So, this epsilon squared will soon get cancelled with the 1 by epsilon squared in k, okay, and the expressions are going to get simpler from this point onwards, okay. But by the way, remember that whenever you do a probabilistic analysis, there is always this confusion as to whether you should keep track of the probability of the good event or the bad event. Answer is always do whatever is convenient. In this case, we are actually keeping track of the probability of the bad event, but usually when you keep track of the probability of a bad event, we keep an upper bound on the probability. We want to show that the bad event happens with very small probability. If you are keeping track of the probability of the good event, we will keep track of a lower bound. So, in this case, bad event is that the projection's length is very different from the original length. That probability is the bad event, we are keeping an upper bound, okay. Now, remember, we are not satisfied if you approximate one length. Our claim was that we will preserve every pairwise length, okay. So, there are n choose 2 different lengths to be worried about, but thankfully we have a union bound which is a weak kind of a bound, but its power lies in the fact that it is assumption free. You really do not need any assumption between these events to use union bound. If A1, A2, A3 etc. are some events, and the probability that their union happens is upper bounded by the sum of their probabilities, right. That is all that we are going to use. So, here how many bad events can happen? Maybe the distance between x1 and x2 was not approximated correctly, that is one bad event. Maybe the distance between x1 and x3 was not approximated correctly, that is a second bad event. Similarly, you have n choose 2 potential bad events, right. In fact, they are not independent. If you can kind of think depending on the dimension, if some very good number of them are approximated correctly, the remaining may also automatically fall in place. But we are not going to make use of any such detailed geometric argument. We are just going to say that we have to approximate not just one, but n choose 2 distances all at the same time. So, none of these bad events should happen, okay. But what is the probability that at least one such bad event will happen? It is n choose 2 times the probability of one of the bad events, okay. Number of bad events times an upper bound on the probability of each bad event, that is what is happening here. But before you read the formula, make sure that you understand what is inside this probability, okay. This is there exists is a union, okay. So, we are analyzing the probability that there exists at least one pairwise distance which is not approximated correctly. That is what this says, right. There exists at least one pairwise distance which is not approximated well. Okay. So, that is what we are analyzing. What is the complement of this event? Okay. This event is the event that at least one pairwise distance is approximated badly. What is the complement of that event? Yes, every pairwise distance among pairs among points in your data set is approximated well. Okay. That is our final goal. We have to show that that probability is high, but that's enough. It's enough to show that this probability is vanishingly small. Okay, and n choose 2, I am just upper bounding by n squared by 2, 2 and 2 goes off, you will get this expression, right. Now, all that you have to do is to pick a k large enough, so that this becomes very small, as simple as that, right. That is all that is left. You have to pick a k large enough, so that this becomes small. How large a k should we pick? Can you try to work it out? In fact, this calculation is something you should practice. This template of using a concentration inequality and doing that has become so common in computer science. Almost every randomized algorithm, the analysis is going to involve this kind of a thing. How many storages do you need? How many different hash functions do you need? Everything will finally boil down to a calculation like this. So, first thing is that, okay, k should have a 1 by epsilon square. Okay. That at least takes one parameter away from the equation, that 1 by epsilon squared will cancel with this epsilon squared that is already there, right. And you will get something like e raised to minus the remaining portion of k by 8. But if it has to be really small, you have to cancel out this n squared, right. So, e to the power some function of n should cancel out n squared. Okay. So, you can actually differentiate this and see. Should I? Okay, maybe I'll just again wait for another minute for what dependency of n do you need? Is it polynomial in logarithmic in n? Yeah, it's logarithmic in n mainly because it is above, sitting above an e, because e raised to minus log n. Think about natural logarithm for a moment. Okay, it keeps thinking simple. E raised to minus log n is what? E raised to log n is n, e raised to minus log n is 1 by n. Okay. Okay, 1 by n is a very small number, but it cannot cancel n squared. So, what should you do? You should try e raised to minus 2 log n. E raised to minus 2 log n is 1 by n squared, which will cancel this n squared, but it will still leave a 1. Probability of 1 is still large. So, let us take e raised to minus 3 log n. What do you get? 1 by n cube. 1 by n cube will cancel out a n squared and still handsomely have a n in the denominator, which is really good. Okay. So, that is what we want. We will take something like 3 log n, but since there is an 8 already there, you need 24 log n. Okay. That is what I have done here. Okay. This is the k that I have chosen. Okay. I have chosen k is equal to 24 over epsilon squared natural log of n. Okay. Again, do not think of it as any magic. If you actually substitute the expression and try, you will see what kind of bound is needed, right. So, this is where we were at the last slide. All I have done is I have substituted k is equal to this value, and you will get n squared times 1 by n cube, which is 1 by n, which is vanishing when your number of data points is very large. So, we have said that our bad event, which is like there exists even one pairwise distance which is not approximated well, is a vanishingly small probability. And okay, by the way, one thing you should have I should have emphasized earlier is that we are approximating we are talking about approximating length of this xi minus xj or its square, and similarly, so we wanted this f of xi minus xj square, right. But what we actually cared about is the distance after the projection, which is this guy, distance between f of xi and f of xj after the projection, or distance square, right, which is actually this. Okay. Distance in a Euclidean space is just the difference vectors norm squared. But because f is linear, and only because f is linear, f of x minus f of y can be written as f of x minus y. So, it is enough to just analyze lengths of individual vectors, where these individual vectors are these n choose 2 pairwise difference vectors. Okay. This is minor point, you would kind of almost assume that we had already had this picture in mind. Okay. Why I am saying is that there were variants of this projection which are nonlinear mappings, but in nonlinear mappings you have to be careful. It is not enough to analyze how the difference vector gets mapped, right. It will be, you have to analyze it separately. Okay. So, don't worry too much about this. Yeah. So, this is the conclusion. We have shown that the probability that there exists even one pairwise distances which is approximated badly goes down to very close to 0. Hence, the probability that every pairwise distance is well approximated happens with very high probability, right. With very high probability, all the n choose 2 pairwise distances in X are well approximated. Why is that true? That is because measures concentrate. When you add up random variables, their probability distribution tends to be very concentrated around the mean, and we have cooked up this transformation in a way that it mimics adding up scaled random variables and so on. Okay. So, this is the last slide for today. In summary, you start with n data points in a d-dimensional space x1 to xn, and you know it is almost like a magician's trick. You do not even look at what is your data point, you just pull out a random mapping. How do you construct this random mapping? You take a matrix A where each entry is normal 0 1, and it is a k by d matrix, right. And the function or the transformation that you do is you do a mapping from Rd to Rk by taking x to 1 by root k a times x. Okay. This is the mapping independent of the data. And what is the guarantee that JL lemma gives you? It tells you that every pairwise distance is well approximated, or the probability that even one pairwise distances is off is very close to 0. Okay. So, two remarks before I end. As I told you, the original setting of the JL lemma in the version that Johnson and Lindenstrauss actually proposed, it was not the transformation was not created this way. It was not by taking a matrix full of standard normals. They really took a random subspace and then analyzed the projection onto that subspace. The analysis is slightly more significantly more complicated there, but you get an easier analysis here. But can you really interpret this as a projection? Is it still correct to talk of it as a projection? So, in order to be able to call this a projection, we need essentially one extra observation, which is that the rows of the A matrix that you create have to be pairwise orthogonal. They have to be orthogonal to each other, because if you remember about how a projection matrix looks like, it was some B transpose, right, and this columns of B were orthogonal, which means the rows of this will be orthogonal. Now, if you create these, each row of this A matrix, remember, is a spherical Gaussian. So, if you sample independent spherical Gaussians, how likely are they to be orthogonal? And thankfully, the answer turns out to be that when the dimension is very large, the answer is yes, where they are very, very highly likely to be orthogonal. So, the matrix A that you construct will end up with very high probability, it will end up having orthogonal rows. Okay. But so, the orthogonality gets at least tackled with very high probability. But now B, remember, was also orthonormal vectors, right. You needed to scale them to be 1. But this is not of a worry. Okay. Scaling is something which you can do at any time, and in fact we will have we have already set up all the scaling so that lengths are preserved. That is not a big worry. But what is this? Who is playing the role of the second matrix B? Okay. Again, that is only a conceptual thing, right, in the sense like when you represent it as B, you are saying that you are representing the projection in the standard ordered basis. without this multiplication, you are still, what you are getting, remember the projection of x onto some vector space x was inner product x times b1 b1 plus inner product x times b2 b2 plus etc. inner product x times bk bk, where b1 b2 bk was an orthonormal basis, right. What is this b1 b2 b3 bk doing here? That's only kind of telling you that this is scale factors associated to this b1 b2 bk. So if you want to get your answer in terms of the standard ordered basis, you have to do that. But if you are okay with your answer being expressed in the basis of b1 b2 b3, then the vector itself is just this, okay, just that you have done a change of basis, okay. So when you are multiplying with A, you can as well do an A transpose A and then say that now you have represented the answer in standard ordered basis, but you would really not want to do that. You will even have blown up the dimension back again, okay. You would rather represent it as coefficients of b1 b2 bk, okay. So once more, this is not really a projection, but with very high probability it is a projection, because the rows tend to be orthogonal. Making it orthonormal is a matter of scaling, it does not really affect anything, but the representation is in terms of this the new basis for the smaller dimensional space, okay. So it is approximately yes with very high probability. Okay. And the second remark that I wanted to say is that we constructed the matrix using standard Gaussians. You can just use Bernoulli plus 1 minus 1. Each entry of the matrix could be a plus 1 or minus 1 with probability half each, and the independence is needed, okay. So this makes computation way more faster because you do not have to do any multiplication. I think Ravindran also mentioned probably, or Venkatesh mentioned it in one of the talk. Proof is more complicated because you do not have the property that linear combination of Bernoullis are Bernoullis. So that part, the proof becomes a bit more difficult, but it's also a well famous and well proved result. So you can also use Bernoulli plus 1 minus 1, okay. Yeah, so that's for any questions. So yeah, thank you for listening so well, for responding so well during all the talks.